Introduction. As we have discussed, in the physical storage unit, access structures are concerned with how records are organized in files, and based on a specific structure, what access methods may be used. A heap file, for example, provides no special access structure, and therefore, we can only have sequential, linear access to records. A hash file, on the other hand, organizes records using one or more hash functions, and the placement of records is based on the values of their hash field. This structure allows us to directly access records if the hash field values are known. In this unit, we will introduce some new access structures called indexes, which are used to speed up the retrieval of records if certain requirements on search conditions are met. An index for a file of records works just like an index catalog in a library. In a normal library environment, for example, there should be catalogs such as author indexes and book title indexes. A user may use one of these indexes to quickly find the location of a required book if he or she knows the author or title of the book. Each index access structure offers an access path to records. Some types of indexes, called secondary access paths, do not affect the physical placement of records on disk. Rather, they provide alternative search paths for locating the records efficiently based on the indexing fields. Other types of indexes can only be constructed on a file with a particular primary organization. In general, any of the structures discussed in physical storage can be used to construct a secondary access path. However, the most common types of indexes are based on sorted file organizations, example, single-level indexes, and tree data structures, example, multi-level indexes, B-trees, and B-plus trees. Indexes can also be created using hashing techniques. The focus of our study in this unit will be on the following: primary indexes, clustering indexes, secondary indexes, multi-level indexes, B-tree and B-plus tree structures. It must be emphasized that different indexes have their own advantages and disadvantages. There is no universally efficient index. Each technique is best suited for a particular type of database applications. The merits of indexes can be measured in the following aspects. Access types. The kind of access methods that can be supported efficiently, example, value-based search or range search. Access time. Time needed to locate a particular record or a set of records. Insertion efficiency. How efficient is an insertion operation? Deletion efficiency. How efficient is a deletion operation? Storage overhead. The additional storage requirement by an index structure. It is worth noting that a file of records can have more than one index. Just like for books, there can be different indexes such as author index and title index. An index access structure is usually constructed on a single field of record in a file called an indexing field. Such an index typically stores each value of the indexing field, along with a list of pointers to all disk blocks that contain records with that field value. The values in the index are usually sorted, ordered, so that we can perform an efficient binary search on the index. To give you an intuitive understanding of an index, we look at library indexes again. For example, an author index in a library will have entries for all authors whose books are stored in the library. Author is the indexing field, and all the names are sorted according to alphabetical order. For a particular author, the index entry will contain locations, that is, pointers, of all the books this author has written. If you know the name of the author, you will be able to use this index to find his or her books quickly. What happens if you do not have an index to use? This is similar to using a heap file and linear search. You will have to browse through the whole library looking for the book. An index file is much smaller than the data file, and therefore, searching the index using a binary search can be carried out quickly. Multi-level indexing goes one step further, in the sense that it eliminates the need for a binary search by building indexes to the index itself. We will be discussing these techniques later on in the unit. Single-level ordered indexes. There are several types of single-level ordered indexes. A primary index is an index specified on the ordering key field of a sorted file of records. If the records are sorted not on the key field but on an on-key field, an index can still be built, which is called a clustering index. The difference lies in the fact that different records have different values in the key field, but for a non-key field, some records may share the same value. It must be noted that a file can have at most one physical ordering field. Thus, it can have at most one primary index or one clustering index, but not both. A third type of index is called secondary index, can be specified on any non-ordering field of a file. A file can have several secondary indexes, in addition to its primary access path, that is, primary index or clustering index. As we mentioned earlier, secondary indexes do not affect the physical organization of records. Primary index. A primary index is built for a file, the data file, sorted on its key field, and itself is another sorted file, the index file, whose index records are of fixed length with two fields. The first field is of the same data type as the ordering key field of the data file, and the second field is a pointer to a disk block, that is, the block address. The ordering key field is called the primary key of the data file. There is one index entry, that is, index record, in the index file for each block in the data file. Each index entry has the value of the primary key field for the first record in a block, and a pointer to that block as its two field values. We use the following notation to refer to an index entry I in the index file. K, I, P, I. K, I is the primary key value, and P, I is the corresponding pointer, that is, block address. For example, to build a primary index on the sorted file shown in Figure 7.1, this is the same student file as we saw in the physical storage unit. We use the ID as primary key because that is the ordering key field of the data file. Each entry in the index has an ID value and a pointer. The first three index entries of such an index file are as follows. K1 equals 9,701,654. P1 equals address of block 1. K2 equals 9,702,381. P2 equals address of block 2. K3 equals 9,703,501. P3 equals address of block 3. Figure 7.2 depicts this primary index. The total number of entries in the index is the same as the number of disk blocks in the data file. In this example, there are B blocks. The first record in each block of the data file is called the anchor record of that block. A variation to such a primary index scheme is that we could use the last record of a block as the block anchor. However, the two schemes are very similar, and there is no significant difference in performance. Thus, it is sufficient to discuss just one of them. A primary index is an example of a sparse index, in the sense that it contains an entry for each disk block rather than for every record in the data file. A dense index, on the other hand, contains an entry for every data record. In the case of a dense index, it does not require the data file to be a sorted file. Instead, it can be built on any file organization, typically a heap file. By definition, an index file is just a special type of data file of fixed-length records with two fields. We use the term index file to refer to data files storing index entries. The general term data file is used to refer to files containing the actual data record such as student. Performance issues. The index file for a primary index needs significantly fewer blocks than does the file for data records for the following two reasons. There are fewer index entries than there are records in the data file because an entry exists for each block rather than for each record. Each index entry is typically smaller in size than a data record because it has only two fields. Consequently, more index entries can fit into one block. A binary search on the index file, hence, requires fewer block accesses than a binary search on the data file. If a record whose primary key value is k is in the data file, then it has to be in the block whose address is pi, where k plus 1. The ith block in the data file contains all such records because of the physical ordering of the records based on the primary key field. For example, look at the first three entries in the index in figure 7.2. K1 equals 9,701,654. P1 equals address of block 1. K2 equals 9,702,381. P2 equals address of block 2. K3 equals 9,703,501. P3 equals address of block 3. The record with ID equals 9,702,399 is in the second block because K2 9,702,399, K3. In fact, all the records with an ID value between K2 and K3 must be in block 2 if they are in the data file at all. To retrieve a record, given the value k of its primary key field, we do a binary search on the index file to find the appropriate index entry, I and n. Use the block address contained in the pointer, pi, to retrieve the data block. The following example explains the performance improvement in terms of the number of block accesses that can be obtained through the use of primary index. A major problem with the primary index is insertion and deletion of records. We have seen similar problems with sorted file organizations. However, they are more serious with the index structure because, if we attempt to insert a record in its correct position in the data file, we not only have to move records to make space for the newcomer, but also have to change some index entries, since moving records may change some block anchors. Deletion of records cause similar problems in the other direction. Since a primary index file is much smaller than the data file, storage overhead is not a serious problem. Clustering indexes. If records of a file are physically ordered on an on-key field which may not have a unique value for each record, that field is called the clustering field. Based on the clustering field values, a clustering index can be built to speed up retrieval of records that have the same value for the clustering field. Remember the difference between a primary index and a clustering index. A clustering index is also a sorted file of fixed-length records with two fields. The first field is of the same type as the clustering field of the data file, and the second field is a block pointer. There is one entry in the clustering index for each distinct value of the clustering field containing the value, and a pointer to the first block in the data file that holds at least one record with that value for its clustering field. Figure 7.3 illustrates an example of the student file sorted by their level rather than ID with a clustering index. In figure 7.3, there are 4 distinct values for level 0, 1, 2, and 3. Thus, there are 4 entries in the clustering index. As can be seen from the figure, many different records have the same level number and can be stored in different blocks. Both level 2 and level 3 entries point to the third block because it stores the first record for level 2 as well as level 3 students. All other blocks following the third block must contain level 3 records because all the records are ordered by level. Performance issues. Performance improvements can be obtained by using the index to locate a record. However, the record insertion and deletion still causes similar problems to those in primary indexes, because the data records are physically ordered. To alleviate the problem of insertion, it is common to reserve a whole block for each distinct value of the clustering field. All records with that value are placed in the block. If more than one block is needed to store the records for a particular value, additional blocks are allocated and linked together. To link blocks, the last position in a block is reserved to hold a block pointer to the next block. If there is no following block, then the block pointer will have the null value. Using this linked block structure, no records with different clustering field values can be stored in the same block. It also makes insertion and deletion more efficient than without the link structure. More blocks will be needed to store records, and some spaces may be wasted. That is the price to pay for improving insertion efficiency. Figure 7.4 explain the scheme. A clustering index is another type of sparse index, because it has an entry for each distinct value of the clustering field rather than for every record in the file. Secondary indexes. A secondary index is a sorted file of records, either fixed length or variable length with two fields. The first field is of the same data type as an indexing field, that is, a non-ordering field on which the index built. The second field is either a block pointer or a record pointer. A file may have more than one secondary index. In this section, we consider two cases of secondary indexes. The index access structure is constructed on a key field. The index access structure is constructed on a non-key field. Index on a key field. Before we proceed, it must be emphasized that a key field is not necessarily an ordering field. In the case of a clustering index, the index built on a non-key ordering field. When the key field is not the ordering field, a secondary index can be constructed on it, where the key field can also be called a secondary key, in contrast to a primary key, where the key field is used to build a primary index. In such a secondary index, there is one index entry for each record in the data file, because the key field, that is, the indexing field, has a distinct value for every record. Each entry contains the value of the secondary key for the record, and a pointer either to the block in which the record is stored, or to the record itself. A pointer to an individual record consists of the block address and the record's position in that block. A secondary index on a key field is a dense index, because it includes one entry for every record in the data file. We again use notation K, I, P, I to represent an index entry. All index entries are ordered by value of K, I, and therefore a binary search can be performed on the index. Because the data records are not physically ordered by values of the secondary key field, we cannot use block anchors, as in primary indexes. That is why an index entry is created for each record in the data file, rather than for each block. Pi is still a block pointer to the block containing the record with the key field value K, I. Once the appropriate block is transferred to main memory, a further search for the desired record within that block can be carried out. A secondary index usually needs more storage space and longer search time than does a primary index, because of its larger number of entries. However, much greater improvement in search time for an arbitrary record can be obtained by using the secondary index, because we would have to do a linear search on the data file if the secondary index did not exist. For a primary index, we could still use a binary search on the main data file, even if the index did not exist. Example 2 explains the improvement in terms of the number of blocks accessed when a secondary index is used to locate a record. Index on a non-key field. Using the same principles, we can also build a secondary index on a non-key field of a file. In this case, many data records can have the same value for the indexing field. There are several options for implementing such an index. Option 1. we can create several entries in the index file with the same KI value. One for each record sharing the same KI value. The other field PI may have different block addresses, depending on where those records are stored. Such an index would be a dense index. Option 2. Alternatively, we can use variable length records for the index entries with a repeating field for the pointer. We maintain a list of pointers in the index entry for KI. One pointer to each block that contains a record whose indexing field value equals KI. In other words, an index entry will look like this. KI, PI, 1, PI, 2, PI, 3. In either option 1 or option 2, the binary search algorithm on the index must be modified appropriately. Option 3. This is the most commonly adopted approach. In this option, we keep the index entries themselves at a fixed length and have a single entry for each indexing field value. Additionally, an extra level of indirection is created to handle the multiple pointers. Such an index is a sparse scheme, and the pointer PI in index entry, KI, PI points to a block of record pointers. This is the extra level. Each record pointer in that block points to one of the data file blocks containing the record with value KI for the indexing field. If some value KI occurs in too many records so that their record pointers cannot fit in a single block, a linked list of blocks is used. Figure 7.5 explains this option. From Figure 7.5, it can be seen that, instead of using index entries like KI, PI, 1, PI, 2, PI, 3, and KJ, PJ, 1, PJ, 2, PJ, 3, as in option 2, an extra level of data structure is used to store the record pointers. Effectively, the repeating field in the index entries of option 2 is removed, which makes option 3 more appealing. It should be noted that a secondary index provides a logical ordering on the data records by the indexing field. If we access the records in order of the entries in the secondary index, the records can be retrieved in order of the indexing field values. The principle. The index structures that we have studied so far involve a sorted index file. A binary search is applied to the index to locate pointers to a block containing a record or records in the file with a specified indexing field value. A binary search requires ELOG2BIU block accesses for an index file with BI blocks, because each step of the algorithm reduces the part of the index file that we continue to search by a factor of 2. This is why the log function to the base 2 is used. Also see Activity 2 in the physical storage unit. The idea behind a multi-level index is to reduce the part of the index that we have to continue to search by BFRI, the blocking factor for the index, which is almost always larger than 2. Thus, the search space can be reduced much faster. The value of BFRI is also called the fan-out of the multi-level index, and we will refer it by the notation FO by analogy to the binary search. Searching a multi-level index requires ELOGFOBIU block accesses, which is a smaller number than for binary search if the fan-out is bigger than 2. The structure. A multi-level index considers the index file, which was discussed in the previous sections, as single-level ordered indexes, and will now be referred to as the first or base level of the multi-level structure, as a sorted file with a distinct value for each KI. Remember, we mentioned earlier that an index file is effectively a special type of data file with 2 fields. Thus, we can build a primary index for an index file itself, that is, on top of the index at the first level. This new index to the first level is called the second level of the multi-level index. Because the second level is a primary index, we can use block anchors so that the second level has one entry for each block of the first level index entries. The blocking factor BFRI for the second level and for all subsequent levels is the same as that for the first level index, because all index entries are of the same size. Each has one field value and one block address. If the first level has R1 entries and the blocking factor, which is also the fan-out, for the index BFRI equals FO, then the first level needs R1/FOU blocks, which is therefore the number of entries R2 needed at the second level of the index. The above process can be repeated, and a third level index can be created on top of the second level one. The third level, which is a primary index for the second level, has an entry for each second level block. Thus, the number of third level entries is R3 equals R2/FOU. Important note: we require a second level only if the first level needs more than one block of disk storage, and similarly, we require a third level only if the second level needs more than one block. We can continue the index building process until all the entries of some index level D fit in a single block. This block at the DTH level is called the top index level. The first level is at the bottom, and we work our way up. Each level reduces the number of entries at the previous level by a factor of FO, the multi-level index fan-out, so we can use the formula 1R1/FOD to calculate D. Hence, a multi-level index with R1 first level entries will need D levels, where D equals ELOGFOR1U. Important: the multi-level structure can be used on any type of index, whether it is a primary, a clustering, or a secondary index, as long as the first level index has distinct values for KI and fixed length entries. Figure 7.6 depicts a multi-level index built on top of a primary index. It should be noted that we could also have a multi-level primary index, which could be sparse. In this case, we must access the data block from the file before we can determine whether the record being searched for is in the file. For a dense index, this can be determined by accessing the first level index without having to access the data block, since there is an index entry for every record in the file. As seen earlier, a multi-level index improves the performance of searching for a record based on a specified indexing field value. However, the problems with insertions and deletions are still there, because all index levels are physically ordered files. To retain the benefits of using multi-level indexing, while reducing index insertion and deletion problems, database developers often adopt a multi-level structure that leaves some space in each of its blocks for inserting new entries. This is called a dynamic multi-level index, and is often implemented by using data structures called B-trees and B-plus trees, which are to be studied in the following sections. A B-tree is a search tree with some additional constraints on it. The additional constraints ensure that the tree is always balanced, and that the space wasted by deletion, if any, never becomes excessive. For a B-tree, however, the algorithms for insertion and deletion become more complex in order to maintain these constraints. Nonetheless, most insertions and deletions are simple process. They become complicated when we want to insert a value into a node that is already full, or delete a value from a node which is just half full. The reason is that not only a B-tree must be balanced, but also a node in the B-tree, except the root, cannot have too many, a maximum limit, or too few, have the maximum search values. Definition of a B-tree. The definition: A B-tree of order P is a tree with the following constraints. Each internal node is of the form P1, K1, PR1, P2, K2, PR2, PQ1, KQ1, PRQ1, PQ, where QP. Each PI is a tree pointer, a pointer to another node in a B-tree. Each PRI is a data pointer, a pointer to the block containing the record, whose search field value is equal to KI. Within each node, K1, K2, KQ1. For all search key field values, x, in the subtree pointed at by pi, we have each node has at most p tree pointers, and p1 search key values. P is the order of the tree, and is the maximum limit. Each node, except the root and leaf nodes, has at least p/2 tree pointers, and p/2-1 search key values, that is, must not be less than half full. The root node has at least 2 tree pointers, 1 search key value, unless it is the only node in the tree. A node with q tree pointers, qp, has q1 search key field values, and hence has q1 data pointers. All leaf nodes are at the same level. They have the same structure as internal nodes except that all of their tree pointers pi are null. A B tree starts with a single root node at level 0. Once the root node is full with p1 search key values, an insertion will cause an overflow, and the node has to be split to create 2 additional nodes at level 1, that is, a new level is created. Only the middle key value is kept in the root node, and the rest of the key values are redistributed evenly between the 2 new nodes. When a non-root node is full, and a new entry is inserted into it, that node is split to become 2 new nodes at the same level, and the middle key value is moved to the parent node, along with 2 tree pointers to the split nodes. If such a move causes an overflow in the parent node is also split in the same way. Such splitting can propagate all the way to the root node, creating a new level every time the root is split. We will study the algorithms in more details when we discuss B plus minus tree later on. Deletion may cause an underflow problem where a node becomes less than half full. When this happens, the node which becomes underflow may obtain some extra values from its adjacent node by redistribution, or may be merged with one of its adjacent nodes if there are not enough values to redistribute, and this can also propagate all the way to the root. Hence, deletion can reduce the number of tree levels. It has been shown by analysis and simulation that, after numerous random insertions and deletions on a B tree, the nodes are approximately 69% full when the number of values in the tree stabilizes. Example. This is also true of B plus minus trees. If this happens, node splitting and merging will occur rarely, so insertion and deletion become quite efficient. If the number of values increases, the tree will also grow without any serious problem. Most implementations of a dynamic multilevel index use a variation of the B tree data structure, called a B plus minus tree. In a B tree, every value of the search field appears once, at some level, in the tree, along with a corresponding data pointer. In a B plus minus tree, data pointers are stored only at the leaf nodes of the tree, hence, the structure of leaf nodes differs from that of internal nodes. The leaf nodes have an entry for every value of the search field, along with a corresponding data pointer to the block containing the record with that value, if the search field is a key field. For a non-key search field, the pointer points to a block containing pointers to the data file records, creating an extra level of indirection, as we have seen before. The leaf nodes of a B plus minus tree are usually linked together to provide ordered access on the search field to the records. These leaf nodes are similar to the first level of the multilevel index. Internal nodes correspond to the other levels of the multilevel index. Some search field values from the leaf nodes are duplicated in the internal nodes to guide the search. The structure of the internal nodes of a B plus minus tree of order P is defined as follows. Each internal node is of the form P1, K1, P2, K2, PQ1, KQ1, PQ, where QP and each PI is a tree pointer. Within each internal node, K1, K2, KQ1, Q. For all search field values, X, in the subtree pointed at by PI, we have each internal node has at most P tree pointers and P1 search key values. Each internal node, except the root, has at least p/2 tree pointers and p/2-1 search key values, that is, must not be less than half full. The root node has at least 2 tree pointers, 1 search key value, if it is an internal node. An internal node with q tree pointers, q equals p, has q1 search key field values. The structure of the leaf nodes of a B ± tree of order P is defined as follows. Each leaf node is of the form K1, PR1, K2, PR2, KQ1, PRQ1, next. Where Q equals P, each PRI is a data pointer, and P next points to the next leaf node of the B ± tree. Within each leaf node, K1, K2, KQ1. Each PRI is a data pointer pointing to the record whose search field value is KI, or to a file block containing the record, or to a block of record pointers that point to records whose search field value is KI if the search field is not a key. Each leaf node has at least p/2 values entries. All leaf nodes are at the same level. Performance issues. Because entries in the internal nodes just contain search values and tree pointers without any data pointers, more entries can be accommodated into an internal node of a B ± tree than for a similar B tree. Thus, for the same block node size, the order P can be larger for the B ± tree than for a B tree. This can lead to fewer B ± tree levels and therefore improve search time. Because structures of internal nodes and leaf nodes are different, their orders can be different. Generally, the order P is for the internal nodes, and leaf nodes can have a different order, denoted as P-leaf, which is defined as being the maximum number of data pointers in a leaf node. Search, insertion, and deletion with B ± trees. To search for a record based on a specified search field value, K, we always start from the root of the B ± tree. Compare K with the value stored in the root until we find the first KI, where K equals KI. Then, follow the tree pointer PI to the next level. If no such KI is found, then follow the rightmost pointer PQ to the next level. We assume that the root is not the only node in the tree. Otherwise, follow the search procedure for a leaf node. If the node at the next level is still an internal node, we repeat the above procedure until we reach the leaf level. Within a leaf node, we search for a stored value, KI, that equals K. If found, we follow its data pointer PRI to retrieve the data block. Otherwise, the desired record is not in the file. Dealing with overflow. When a leaf node overflows because of insertion of a new entry, it must be split. The first entries in the original node are kept there, and the rest are moved to a new leaf node, just created. The original P next pointer is changed and points to the new leaf node, and the same pointer new P next in the new node will have the original value of P next. The MTH search value is duplicated in the parent node, an internal node, and an extra pointer to the new node is created in the parent. If the above move of value causes overflow in the parent node, because the parent node is already full, then it must also split. The entries in the internal node now overflowed up to Pn, the NTH tree pointer, after inserting the new value, and pointer, where n equals P plus 1 divided by 2, are kept, while the NTH search value is moved to the parent, not duplicated. A new internal node will now hold the entries from Pn plus 1 to the end of the entries in the overflowed node. This splitting can propagate all the way up to create a new root node, and hence a new level for the B plus tree. When an entry is deleted, it is always removed from the leaf level. If it happens to occur in an internal node, because it is the rightmost value of a subtree, then it must also be removed from there. In this case, the value to its left in the leaf node will replace it in the internal node, because that node is now the rightmost entry in the subtree. If deletion causes underflow, we will try to find an adjacent leaf node and redistribute the entries among the two nodes so that both can become at least half full. If we cannot find such an adjacent node with enough entries, then we will merge them. In this case, the number of leaf nodes is reduced. If a merge between two nodes is not possible because of insufficient number of entries, we may merge 3 leaf nodes into 2. In merge cases, underflow may propagate to internal nodes because one fewer tree pointer and search value are needed. This can propagate to the root and reduce the tree levels. B times minus tree. A variation of B tree and B plus tree. Recall that the definitions of B tree and B plus tree require each node to be at least half full. Such a requirement can be changed to require each node to be at least 2/3 full. In this case, the B tree is called a B times minus tree. This can improve the retrieval performance a little further without incurring too many overheads on maintaining the tree. Indexes can be used to gain faster access to data in databases. Thus, all commercial database management systems, DBMS, such as Oracle, Ingres, Sybase, etc., incorporate such access structures. In these DBMS, however, the presence of an index is transparent to the ordinary users. Users will not have any control over what index structures should be used and what algorithms should be applied. These have all been determined by the DBMS. In Oracle, for example, indexes are built by using the B times minus tree structure. Algorithms necessary for maintaining such indexes have all been implemented and tuned in Oracle to gain the maximum efficiency. After an index has been created for a table, that is, a file of records, Oracle automatically maintains that index. Insertions, modifications, and deletions of rows in the table, that is, records in a file, automatically update the related indexes. Although, in practice, users do not have much control over the physical aspects of indexes, they can specify whether or not they want to create an index on a table, and if so, what attribute or attributes should be the indexing field s. In Oracle, a table can have any number of indexes, at most one primary or clustering index, plus any number of secondary indexes. However, it is important to remember that more indexes there are, the more overhead is incurred during table modifications, insertions, and deletions. In order to study the practical use of indexes, we will use Oracle as an example throughout the rest of this unit. Types of indexes in Oracle. So far in this unit, the indexes we have studied are all based on a single indexing field. In Oracle, another type of index is also allowed. That is, the so-called composite index, which builds an access path based on several columns, fields in a table. In other words, there is an index entry for a distinct combination of values in those columns. When creating such an index, the order of the columns in the definition is important, because the index is accessed based on that order. Deciding what to index. An index should always be created with some knowledge of the database application and data access patterns. If an index is created on a column that is not used to access data, the index is useless. In short, indexes should be created based on the values accessed in the application. The application should be developed to take advantages of these indexes. Having knowledge of and influence over these indexes can be very useful to the application developer. What to index? An index is effective only when it is used. In order to minimize the overhead in maintaining indexes, we need to be selective. What tables need indexes? Create indexes on tables when most queries select only a small number of rows from those tables. Queries that select a large number of rows defeat the purpose of indexing. Use indexes when queries access less than 5% of the rows in the table. Do not build indexes on tables that are frequently updated. Create indexes on tables that do not have duplicate values on the columns, usually selected in where clause, that is, a large number of distinct values, in the indexing field will help. Tables in which the selection is based on true or false values are not good candidates for indexing. Build indexes on tables that are queried with relatively simple where clause. Complex where clauses may not take advantages of indexes. Which column should be used as the indexing field? Choose columns that are most frequently specified in where clauses. Do not use columns that do not have many distinct values. Columns in which a large percentage of rows are duplicates cannot take advantages of indexing. Columns that have unique values are good candidates for indexing. Oracle automatically indexes columns that are unique or are primary keys. Columns that are commonly used to join tables are good candidates for indexing. Frequently updated columns should not be used. When to use composite indexes. When two or more columns do not have unique values individually, but their value combinations are unique, a composite index using these columns is very effective. If a table has a composite key, a corresponding composite index could be created. If all values of a select statement are in a composite index, Oracle does not query the actual table. The result is returned from the index. Taking advantages of indexes. Once indexes have been created, it is necessary to include the indexed column or columns in the where clause of the SQL statements. When the indexed column or columns are referenced in the where clause, the Oracle Query Optimizer will immediately know to use an appropriate index to perform the search rather than carry out a complete table scan to access the requested data. If the indexed columns are not included, the index structure will be bypassed, and it will cause a time-consuming table scan. It takes the right application coding to take advantages of indexes. Coordinations between the DBA, database administrator, and the application developers are required to achieve the objective.